Bismillahirrahmanirrahim. In this lecture, I am solving problem 6.9 from the book Applied Thermodynamics by McConkey. So the statement of the problem is air and carbon monoxide are mixed in the proportion 3:1 by mass. The carbon monoxide is supplied at 4 bar and 15 degrees centigrade, and the air is supplied at 7 bar and 32 degrees centigrade. So first I write given data. So in given data, air mass ratio of mass of air to mass of carbon monoxide is 3:1. It means that if mass of carbon monoxide is 1 kilogram, then mass of air will be 3 kilogram. The carbon monoxide is supplied at 4 bar and 15 degrees centigrade. Pressure of carbon monoxide is 4 bar. We can write 4 bar is 4 multiplied by 10 power 5 Pascal or Newton per square meter. And temperature per carbon monoxide is 15 degrees centigrade. Convert this into Kelvin, which is equal to 15 plus 273 Kelvin, which is equal to 288 Kelvin. And the air is supplied, so pressure of air is equal to at 7 bar, and 7 bar is equal to 7 multiplied by 10 power 5 Pascal, and Pascal is equal to Newton per square meter. And temperature is 32 degrees centigrade. So temperature of air is equal to 32 degrees centigrade. Convert this into Kelvin, which is equal to 32 plus 273 Kelvin, which is equal to 305 Kelvin. The two constituents are fast and steady flow through non-return wall to mix adiabatically. It means that the two gases are mixed adiabatically at a pressure of 1 bar. It means that process is adiabatic mixing. Adiabatic mixing. And pressure of the mixture is equal to 1 bar, and 1 bar is equal to 1 multiplied by 10 power 5 Newton per square meter. Calculate number 1 the final temperature of the mixture. Required is first point the final temperature of the mixture. Number 2 the partial pressure of each constituents of the mixture. It means that partial pressure of in air there is nitrogen and oxygen, 75% nitrogen and 21% oxygen. It means that find partial pressure of nitrogen, which is available in the air, 79%, and pressure of oxygen, which is in air, 21%, and pressure of carbon monoxide. Number 3 the increase of entropy per kilogram of mixture. Number 3 find increase in entropy per kilogram means specific entropy. Number 4 the volume flow of mixture per a flow of 1 kilogram per minute of carbon monoxide. Volume flow rate for the mixture. Find volume flow rate for the mixture, and for carbon monoxide mass flow rate is 1 kilogram per minute. Mass flow, it is given to us. Mass flow rate for carbon monoxide is 1 kilogram per minute. 1 kilogram per minute. And number 5 find the velocity of mixture if the area of the pipe downstream of the mixing section is 0.1 square meter. It means that find the velocity of the mixture velocity of the mixture, and area after mixing the air and carbon monoxide. The area is 0.1 square meter. Area is equal to 0.1 square meter. There are some assumptions. Assumption is, assume that air contain 79% nitrogen and 21% oxygen. And there are some constant values which we will use in the solution of this problem. So we know that Cp per year is equal to 1.005 kilojoule per kilogram per Kelvin, and mass Cp per carbon monoxide is equal to 1.04 kilojoule per kilogram per Kelvin. Mass flow rate of air is equal to 28.96 kilogram per kilomole, and mass flow rate of carbon monoxide is 28 kilogram per kilomole. Similarly, R for air is equal to 8.3144 kilojoule per kilomole per Kelvin, and R for carbon monoxide is equal to 0.2968 kilojoule per kilogram per Kelvin. And this is the this is molar gas constant, not this is molar gas constant or universal gas constant. And R per year, ideal gas constant per year is 0.287 kilojoule per kilogram per kilo. We can write this as 287 joule per kilogram multiplied by kilo, and kilo is equal to 1000, so this will be equal to 287 per kilogram per Kelvin. Now we are starting the solution. So first we find temperature of the mixture after mixing the carbon monoxide and air. So we have the formula: mass of carbon monoxide multiplied by specific heat capacity at constant pressure per carbon monoxide multiplied by temperature of carbon monoxide plus mass of air multiplied by Cp per year multiplied by temperature per year is equal to mass of carbon monoxide plus mass of air into temperature of the Cp per the mixture and temperature per the mixture. Basically this formula is M1Cp1T1 plus M2Cp2T2 is equal to M1 plus F2 and Cp and T of the mixture. This is formula. Now we have to find the temperature of the mixture, but first we find Cp of the mixture is not given to us. First we find Cp per the mixture. So Cp per the mixture is equal to there are two gases in the mixture. One is carbon monoxide and other is air. So mass of carbon monoxide multiplied by Cp of carbon monoxide plus mass of air multiplied by Cp of air divided by total mass of CO plus mass of carbon monoxide. So Cp per mixture is equal to mass of carbon monoxide is 1 kg multiplied by Cp per carbon monoxide is 1.04 kilojoule per kilogram per Kelvin plus mass of air is 3 kg ratio 3 ratio 1. So 3 kilogram is per air and 1 kilogram is per carbon monoxide. Cp per air is 1.005 kilojoule per kilogram divided by mass of carbon monoxide 3 kg plus 1 kg. So Cp per mixture is equal to, this kilogram will be cancelled with kilogram. 1 multiplied by 1.04 is 1.04 kilojoule per Kelvin plus 3 multiplied by 1.005 is equal to, and this kilogram will be cancelled with this kilogram, and you can multiply and then add. So this simplification is very simple, not difficult. So 4.055 kilojoule per Kelvin divided by 4 kilogram. So Cp per mixture will be 4.005 divided by 4 is 1.01375 kilojoule per kilogram per Kelvin. This is per kilogram, this is per Kelvin. Now we can find T of the mixture. So put values in this equation and find the value of T mixture. So T mixture is equal to, rearrange the formula, mass of carbon monoxide Cp per carbon monoxide and temperature per carbon monoxide plus mass of air into Cp of air into temperature of air, all these values are given, divided by mass of Cp plus mass of carbon monoxide into Cp of mixture. So temperature of mixture is equal to, putting values, so mass is 1 kg, Cp per carbon monoxide is 1.04 kilojoule per kilogram per Kelvin, temperature per carbon monoxide is 288 Kelvin plus mass of air is 3 kg multiplied by Cp per air is 1.00405 kilojoule per kilogram per Kelvin, temperature per air is 305 Kelvin divided by mCp, mass of CO, this is not Cp, mass of carbon monoxide. So 1 kg plus 3 kg into Cp of mixture, and Cp of mixture is 1.01375 kilojoule per kilogram per Kelvin. This kilogram will be cancelled with this kilogram. Here Kelvin will be cancelled with Kelvin, and here Kelvin will be cancelled with Kelvin. Kilogram will be cancelled with kilogram. Kilogram will be cancelled with kilogram. So T of mixture, multiply these two values and multiply these two values and then add. So after the addition, this 1 multiplied by 1.04 multiplied by 288 is equal to 299.52 kilojoule plus 3 multiplied by 1.005 and 2305 is 919.575 kilojoule divided by 1 plus 3 is 4, and 4 multiplied by this is equal to 4.055 kilojoule per kilogram per Kelvin. 55 kilojoule per kilogram per. Now add the above two values, which is equal to 1219.95 divided by kilojoule divided by 4.055 kilojoule. Kelvin is already, I think this Kelvin is not, this is already cancelled with, kilogram is already cancelled with kilogram. So this is Kelvin. So kilojoule per Kelvin. Now kilojoule will be cancelled with kilojoule and Kelvin will be in the T of the mixture is equal to in the numerator, because this is a double division. So temperature of the mixture is 300.64 Kelvin. If you want to convert this into degree centigrade, so 300.64 minus 273 degrees centigrade, which is equal to 27.64 degrees centigrade. So this is basically the answer of part number 1. So we solve part number 1, and now we have to find at part number 2 partial pressure of nitrogen and partial pressure of oxygen and partial pressure of carbon monoxide. So for this, we know that in part number 2 we have to find partial pressure of air basically, but air contains nitrogen and oxygen. Therefore partial pressure of air, but air contains two constituents, one nitrogen 79% and one oxygen 21%, already explained in the start of the problem. And partial pressure of carbon monoxide. So we know that molar mass of carbon monoxide, molar mass of oxygen, and molar mass of nitrogen. We already know the molar mass of nitrogen is 28 kilogram per kilomole. Molar mass of oxygen is equal to 32 kilogram per kilomole, and molar mass of carbon monoxide is 28 kilogram per kilomole. Now we have to find the partial number of mole of all these. So number of mole of CO is equal to number of mole of carbon monoxide is equal to molar mass of carbon monoxide divided by molar mass of carbon monoxide. So mass of carbon monoxide is already known to us, which is 1 kg, and molar mass is 28 kilogram per kilomole. Kilogram will be cancelled with kilogram. 1 by 28 is 0.0357 kilomole. This is the number of mole of carbon monoxide. Now per number of mole of nitrogen and oxygen, first we find number of mole of air. So number of mole of air is equal to mass of air divided by molar mass of air. So mass of air is 3 kilogram and molar mass of air is 28.96 kilogram per kilomole. Kilogram will be cancelled with kilogram. 3 divided by 28.96 is 0.13929 kilomole. This is the number of mole of air. Now we can easily find number of mole of carbon monoxide, because we know that carbon monoxide our total number. No need to find the number of mole of carbon dioxide, oxygen and nitrogen. Now total number of mole is equal to number of mole of carbon monoxide plus number of mole of air, which is equal to 0.0357 kilomole plus 0.13929 kilomole. So total number of mole is equal to 0.13929 kilomole, and this is basically 0.10359. Now we can find easily molar fraction. So mole fraction of carbon monoxide is equal to 0.0357 number of mole of carbon monoxide, and total number of mole is 0.13929 kilomole and kilomole, which is equal to 0.256. We can also find this as percentage. Multiply and divide by 100, 25.6%. Similarly, number of mole of air divided by N. number of mole of air is equal to total number of mole is 0.13929 kilomole, and number of mole of air is 0.10359 kilomole, which is equal to 0.7436 0.7436 kilomole will be cancelled with kilomole, and in percent this is equal to 74.36%. Now partial pressure of carbon monoxide. So partial pressure of carbon monoxide is basically mole fraction multiplied by total pressure of the mixture, and total pressure of the mixture is given to us. Number of mole of molar fraction of carbon monoxide multiplied by total pressure of the mixture, which is basically 1 bar. So partial pressure of carbon monoxide is 0.256 multiplied by 1 bar. So which is equal to partial pressure of carbon monoxide is 0.256 bar. Now we are finding partial pressure per air, but air contain 79% nitrogen and 79% nitrogen and 21% oxygen. So now partial pressure of air is equal to number of molar fraction of air multiplied by 1 bar. So molar fraction of air is basically 0.7436 multiplied by 1 bar. So this is equal to partial pressure of air is equal to 0.7436 bar. But basically air contains 79% nitrogen. So partial pressure of nitrogen is equal to 79% means 0.79 multiplied by 0.7436 bar. So partial pressure of nitrogen is equal to 0.587 bar, and partial pressure of oxygen 21% means 0.21 multiplied by 0.7436 bar, which is equal to so partial pressure of oxygen is equal to 0.156 bar. So this is the solution of part number 2. Now in part number 3 we have to find the increase in entropy. So for increase in entropy, as we know, this is adiabatic mixing. So we cannot directly find change in entropy because adiabatic means entropy is constant. So we cannot directly find entropy change. So for this we divide the process in isentropic and and constant pressure and constant volume pressure, something like this. We divide the whole process into, this is from 1 to A and from A to 2. From 1 to A, this is constant pressure process, and per constant pressure process change in entropy is R natural log of V2 divided by V1, and per this is constant volume process. And per constant volume process the change in entropy is a CV natural log of T1 divided by T2. So and this is temperature and degree centigrade, this is entropy and kilojoule per kilogram per Kelvin. So it means that entropy change is equal to R for this, first we found per air, then for carbon monoxide. Per air is equal to R natural log of V2 divided by V1. But this V2 is basically volume of the mixture. And V1 is basically volume of air. And V2 by V1 is not given to us. So This process is isothermal. PV is equal to C, constant temperature process. This is not constant pressure process, but this is constant temperature process. So for constant temperature process, PV is equal to C, or P1 V1 is equal to P2 V2, or V2 divided by V1 is equal to P1 divided by P2. So we can put here, instead of V2 divided by V1, P1 divided by P2, because this is isothermal. P1 V1 is equal to P2 V2 plus CV natural log of T1 divided by T2, and S2 minus S1 per year is equal to R natural log of P1 is basically, this is per year, so initial pressure per year, and P2 is the pressure of mixture, plus CV natural log of T1 is basically temperature of air, and T2 is temperature of mixture. So S2 minus S1 per year is equal to, putting values, R per year is 0.287 kilojoule per kilogram per Kelvin. Pressure per year is, putting values here, so pressure per year is 7 bar, and pressure of mixture is given as 1 bar. Similarly, plus Cb per year is 0.718 kilojoule per kilogram per Kelvin, and this is natural log of temperature of air is 305 Kelvin, and temperature per the mixture is 300.64 Kelvin. Kelvin will be cancelled, bar will be cancelled with bar. Now this is simple calculation. Calculate this per year. So per year this value is 0.5688. This is simple calculation. You can do this, 0.5688 kilojoule per kilogram per Kelvin. Now mass of air is given to us, so find total entropy. So total entropy change per year is equal to mass multiplied by S2 minus S1 per year. So total entropy change per year is equal to, mass is 3 kilogram, and this is 0.5688 kilojoule per kilogram per Kelvin. Kilogram will be cancelled with kilogram. So as total entropy change per year is equal to, specific entropy is equal to total entropy divided by mass. So total entropy is equal to mass multiplied by specific entropy, which is equal to 1.706 kilojoule per Kelvin. Now we are finding entropy change per carbon monoxide. So entropy change per carbon monoxide, the same formula and same figure, TS diagram. So this is equal to R natural log of, so this is R per year. Now here we will use R per carbon monoxide, natural log of pressure per carbon monoxide divided by pressure of mixture, pressure of carbon monoxide divided by pressure of mixture, plus Cv per carbon monoxide, and natural log of temperature, this is T1 per carbon monoxide divided by temperature of the mixture. T2 is basically temperature of the mixture. Now putting values here, R per carbon monoxide is equal to 0.2968 kilojoule per kilogram per Kelvin. Natural log of pressure of carbon monoxide is basically given to us as 4 bar. Pressure of the mixture is 1 bar, plus Cv per carbon monoxide is 0.7437 kilojoule per kilogram per Kelvin. Natural log of temperature per carbon monoxide is 288 Kelvin. Temperature of the mixture is 300.64 Kelvin. So simplify this and find S2 minus S1 for carbon monoxide, which is equal to 0.37955 kilojoule per kilogram per Kelvin. Now total entropy change is 2 minus S1 per carbon monoxide. Mass is basically 1. Mass multiplied by this. So mass is 1 kilogram multiplied by 0.37955 kilojoule per kilogram per Kelvin. Kilogram will be cancelled with kilogram. So total entropy change in carbon monoxide is 0.37955 kilojoule per Kelvin. Now entropy change of the mixture. Entropy change of the mixture is equal to entropy change of the air plus total entropy change of the carbon monoxide, which is equal to, this is basically equal to 1.706. 1.2 minus S1 per year is basically here. Oh, sorry, this is 1.706. 1.706 kilojoule per Kelvin plus per carbon monoxide is 0.37955 kilojoule per Kelvin. So total change entropy of the mixture is equal to 2.08 kilojoule per Kelvin. But we have to find in per kilogram. So specific entropy change of the mixture is equal to total entropy change of the mixture divided by mass. Mass of the mixture means total mass, or mass of the mixture 2.08 kilojoule per Kelvin divided by 4 kilogram. Total mass is 4 kilogram. So change in entropy of the mixture is equal to 0.52138. 0.52138 kilojoule per kilogram per Kelvin. Now this is the solution of part number 3. Now part number 4, volume flow rate of the mixture find, and mass flow rate of carbon monoxide is given to us 1 kilogram per minute. Now first we know that first we find specific volume. Specific volume is equal to R, PV is equal to RT. PV is equal to RT. So V is equal to RT divided by P. RT, and this is V of the mixture. So this is R of the mixture. This is temperature of the mixture, and this is pressure of the mixture. First we find R of the mixture. So R of the mixture is equal to mass per carbon monoxide multiplied by R per carbon monoxide plus mass of air multiplied by R of air divided by mass of mixture. Mass of mixture or total mass. So R of mixture is equal to mass of carbon monoxide is 1 kg. R per carbon monoxide is 0.2968 kilojoule per kilogram per Kelvin. Kilogram will be cancelled with kilogram. Plus mass of air is 3 kg. R per air is 0.287 kilojoule per kilogram per Kelvin. This kilogram will be cancelled with kilogram. Total mass is basically equal to 4 kilogram. Now this is simple calculation and find the value of R. So R of mixture is 0.28945 kilojoule per kilogram per Kelvin. Now we have to find the we can find specific volume. Specific volume is equal to R of the mixture. Already this formula is written by me. Temperature of the mixture divided by pressure of the mixture. PV is equal to RT. So this is equal to 0.28945 and kilojoule. So kilo is equal to 1000 and joule is equal to Newton meter per kilogram per Kelvin. Multiplied by temperature of the mixture is 300.64 Kelvin. This Kelvin will be cancelled with this Kelvin. And pressure is 1 bar. R1 multiplied by 10 power 5 Newton per square meter. So find the specific volume. From this, Newton will be cancelled with Newton, and final answer will be meter cube per kg. This meter square, and this meter is meter cube, and this is per kg. So final answer will be final V is equal to 0.8702 meter cube per kg. But we have to find the volume flow rate. So volume flow rate is equal to mass flow rate multiplied by specific volume of the mixture. So volume flow rate of the mixture, mass flow rate is given to us 1 kilogram per minute, and volume, specific volume is 0.8702 meter per kg, cubic meter per kg. Kilogram will be cancelled with kilogram, and volume flow rate of the mixture is equal to 0.8702. This is basically, total volume, this is 4 kilogram. Volume given to us here is basically mass of carbon monoxide. This is basically mass of carbon monoxide, but we know that the masses of carbon monoxide and air is ratio of 3. It means that mass of air will be 3 kilogram per minute. So total mass flow rate will be 4 kilogram per minute. So here we will use mass, because this is mass of mixture, not mass of carbon monoxide. So this is equal to 3.48 meter cube per minute. Meter cube per minute. This is the answer of part number 4. Now we are finding part number 5. So at part number 5, we required value is basically velocity of the mixture. Velocity of the mixture. And area of the mixture is given to us as 0.1 square meter. Now we know that velocity of the mixture, U is equal to V dot divided by A. A is given to us. Volume flow rate divided by area. U or V. You can represent this by either U or V. U of the mixture is equal to volume flow rate divided by area. So volume, now okay, this is given us as 0.48. Okay, this is given in 3.48 meter cube per minute. Meter cube per minute, and area is equal to 0.1 square meter. Area is equal to 0.1 square meter. So U of mixture is equal to, you have to convert this minute into second. So you can write this as 3 meter cube divided by 1 minute is equal to 60 seconds. So I can write here, instead of 1 minute, 60 seconds in 0.1 square meter. This square meter will be cancelled with square meter, and final answer will be in meter per second. So U of the mixture is equal to 3.48 divided by 60 and divided by 0.1 is equal to 0.58 meter per second. And this is the final solution. And for more problems, please like and subscribe my YouTube channel and share with your friends. Thank you.